12:30 tomorrow, we'll have a town hall / open problem session on the second floor. It's bring your own lunch, so you can go buy lunch and then come back, and then second floor at 12:30.
Sorry.
We will
Say
meet.
that again. What's
12:30 tomorrow. Bring your own lunch. Open problems town hall event on the second floor. All right. With my great pleasure. Yeah.
Very much. Thank you. Okay, so we're going to continue the theory portion of proof systems for the next hour, and then Justin will do the applied part. Okay, so the focus of this hour is going to be on these succinct non-interactive arguments, or SNARGs. So again, for the focus, think about NP languages, though we will talk about deterministic languages as well. So as Alex said, the goal here is we have some NP instance X, we have a long witness, but we don't want to send it, it's too long. Instead, we want to send a succinct certificate, or what we call a SNARG, proof that convinces the verifier that X is indeed in the language. And we assume that the prover and verifier share some common reference string. And that's, as Alex said, that's necessary. So again, as was mentioned last talk, there's two notions of soundness that people care about. We won't be really focused on the distinction between these two in the talk, because I want to kind of show you kind of the big idea, so we won't kind of go into the nitty-gritty, but it's good to keep in mind. There is a non-adaptive soundness and there's adaptive soundness. So in both soundness, we consider only efficient adversary. So we assume the adversary, the cheating prover, is computationally bounded. In the non-adaptive, the cheating prover first needs to choose the statement on which he cheats, and then he should succeed with only negligible probability in convincing the verifier to accept for a randomly chosen common reference string. In the adaptive version, he can choose the statement with which he cheats based on the CRS. So he can choose the statement adaptively based on the CRS. So these are two notions of soundness. Of course, we would prefer the second notion, the adaptive notion. It's strictly stronger, but both are interesting, and we would take what we can get. Okay, so we will focus this hour on trying to construct such SNARGs. Any questions before kind of what? Why is the first one interesting? Because, the fact that you can choose your language based on the CRS, probably it's going to be a contrived statement. Like, okay, usually you want to cheat with something that's meaningful to you, not like, I want to cheat and say, Shafi owes me $1 million. I don't want to cheat with some weird thing that depends on the CRS. What is that thing? Is it meaningful? So in that sense, it's still interesting. But that's a great question. Okay, questions about our goal. So our goal is to construct such SNARGs for NP. Okay. And of course, the holy grail is to do that based on standard assumptions. That's what we really want. So what's known? As Alex said, we know how to do it from I/O. And again, let me just repeat it very briefly. The idea is very simple. The idea is the CRS will contain basically an obfuscation of a circuit that has a secret key in it. It takes X and the witness. It checks that the witness is valid. And if so, it outputs like a certificate that X is in the language. What's a certificate? Like a signature. It signs like, yeah, X is in the language. And then the proof or the certificate chooses a signature. And to verify, all you need is the public key. So the verifier just needs the public key. He says, oh yeah, the CRS signed it. It means it's in the language. Okay? And if this was a really black box, of course, like you don't learn anything, then it's sound. And then Sahai Waters worked a bit to prove that it's sound, even if it's not black box. And then there were further works that made it, the first was a non-adaptive sound, then adaptive sound. But basically, if you're willing to assume I/O, we have a SNARG for NP.
What exactly are you putting in the Yael? Is the verification, is the signing algorithm? What's in the Yael?
What's here? Yeah, so this circuit has a secret key for the signature. Sorry, this should be a signature, a secret key. Sorry, this is a secret key. It's a typo. Yeah, it has a secret key and you sign with respect to the secret key. Sorry, thank you, Daniel.
But in your other
When you said that things are dependent,
Yeah.
I mean, what sense is this independent?
No. So all I'm saying, okay, forget about adaptive, non-adaptive soundness. This CRS is just a CRS that has a secret key in it. You feed him your instance with a witness. It verifies the witness, and if it's a valid witness, it signs it as like, it signs the instance, like saying X is valid.
It's a serious.
No, it's not a CRS of X. The circuit has nothing to do with X. It takes X as an input. It just takes any instance with a witness. If the witness is valid, it signs the instance. Okay, the CRS has nothing to do with the instance.
Sub L?
It's sub L. Yeah, it depends on the language. Yes. Yeah.
It's basically you publish a verifier that anybody can run to check the signature.
Exactly. That's all it is. Exactly.
But if you run, is it designated verifier or something?
No, because anybody can verify the signature. So it's not designated. I mean, if you see a signature, like, oh yeah, the CRS signed it. We trust the CRS. Yeah. So it's publicly verifiable. It's really, has the guarantees we want. So why aren't we happy? Well, what do we want to improve from here? Why aren't we done? So first of all, I/O is not a standard assumption on its own. We recently learned that we can instantiate it based on standard assumptions. But when we instantiate it, the reduction from the security of I/O to these assumptions runs in exponential times, in 2 to the instance length. So that's one negative, and as a result, we need to rely on sub-exponential assumptions. So one negative is that the reduction is exponential time. The other is that the CRS is long and structured. So basically, the CRS, someone needs to generate this I/O circuit. And finally, we don't know how to instantiate I/O based on post-quantum assumptions, maybe heuristically, but not under standard assumptions. So it's not post-quantum secure. So these are 3 things that ideally we would want to improve. Okay, so what is really our dream theorem? My goal is by the end of the summer, we'll give a talk saying we have SNARGs for NP under polynomial hardness of algorithm. Okay, so that's the project for the summer. Okay, so yeah.
If it's sub-exponential hardness, it's not.
What?
If it's just sub-exponential hardness for algebra E, is that good enough?
I'm okay with the sub-exponential, but no, I dream big, Hotek. I want polynomial, but yeah, I will be happy with sub-exponential. Okay.
Non-adaptive.
Okay, why not adaptive?
No, I don't know. I'm asking, what's your dream?
Really, I dream big. Why not? I want polynomial. I want everything. But I will take sub-exponential. I'll take non-adaptive. I'll take anything. Okay. Okay. So those who are more experts in this topic may kind of raise a brow and say, "Wait, there's the impossibility result of Gentry and Wicks," and they say, actually, you have to run. The reduction has to run in exponential time. So this dream of polynomial hardness, forget it. Okay, however, there's 2 caveats to this. First of all, it's only for adaptive soundness. But like Shafi said, we want adaptive sound. It's better, right? So let's hope for adaptive soundness. Secondly, it's only for black box reductions. Now, many of us may think, okay, black box reduction, it's like, come on, it's basically an impossibility result because we don't know how to overcome these black box barriers. And one takeaway I want you to take from this talk is I actually don't believe it's an impossibility result. I really believe it's only a barrier that sheds light to where we need to head in order to get a positive result. And I'm hoping that I'll be able to get there and convince you that actually we have a non-black box technique to our disposal that we can use. Okay, so really it's just an invitation to kind of move to the right direction.
That's why you put this adaptive, non-adaptive.
Well, I put it because it's going to come up in both places, actually. No, the technique I have is only actually for non-adaptive. But the way I'm thinking of using it is for non-adaptive. But it is a non-black box technique. Because we have a non-black box technique in our hand, then, so it's not really an impossibility result. It just says we'll need to use it.
To overcome the barrier, you just need to rule out one of them.
Yes, exactly. Exactly. But ideally, I would want adaptive soundness. And then I need to rule out the non-black box reduction. Okay, so what's the plan for today? What I want to show you today is I'm going to cover kind of 3 pillars of works that have been done in this space. It's not everything by any stretch. So it's, you know, I have only an hour and I had to choose. We had to choose kind of what we focus on. So I'm going to focus on 3 kind of pillars. The first one gives you only designated verifier. So it's not really a full SNARG, like I said. But this kind of attempt uses multi-prover interactive proofs and compiles it using FHE. So I'm going to explain that's kind of the first line of result. Then I'm going to go to the next pillar, which is the hash-and-BARG kind of attempt. By the way, I'm putting here all the references with full names below. I just don't want to spend all my time reading the names, but you know they're here for you to read. And both of these have been kind of very fruitful, but have failed to give us SNARGs for all of NP like we want. And there's a reason for it. Okay, then, and I'll explain why. There's an inherent reason why they don't give us all of NP, rather some P and some subclasses of NP and so on, but not all the way. And then the third pillar, which is a new pillar, it extends this hash-and-BARG approach, which I'll explain what this means, to what we call an encrypt hash-and-BARG. And here, actually, we have no barriers. So this is where I'm kind of hoping to use my kind of our big dream and our non-black box technique and try to go all the way to prove soundness for all of NP under LWE. We're not there yet, but I'm going to show you how close we are, okay, and what's kind of left. Okay, so we're going to start with the first pillar unless there's a question. Okay, so the first part, this dates back to kind of actually a heuristic from 1999 that proposed the following. You know, we have what's called a two-prover, multi-prover interactive proof by Benno, Shafi, Kilian, and Avi Vigdalson. And the idea there, their point is, if you have 2 provers that you believe that they don't interact with, the assumption is they don't interact, proofs can be done very, very efficiently. Or you can just send them a query, get an answer. These are very, very short, like polylogarithmic in the instance. And you're convinced. So we have very short kind of proofs, but if you have 2 provers that don't interact, we want a SNARG, or we want 1 prover. So what's the idea? The idea is, fine, send both queries to 1 prover. But that's no good, because if you just send to 1 prover, they see both queries, soundness breaks down completely. Okay, because really the soundness here really relies on the fact that the provers don't interact and don't see each other's queries. Basically, the idea is you check consistency against one another. That's how these MIP, multi-prover interactive proof, works. So if you see both queries, of course you can cheat consistently. So, you know, no good. So the idea is, well, let's put them under FHE, under encryption, or we'll hide them. So we'll give the prover both queries, this under 1 key, this under a completely different key. So think of it, we put them in different boxes. And what the prover can do, when he takes this box, he can do homomorphic computation, so he can give the answer to this query like this, like prover 1 did, and he can give answer to this query like prover 2 did. And when he answers this query, he has no idea what's sitting here because it's in a different, under a different key. So it's like a different box. So it's a really fabulous heuristic. You know, it's a great idea. And now the question is, it sound? And unfortunately, it's not sound. And that's a bit surprising that it's not sound, because intuitively it seems like it should be sound. So why isn't it sound? Why, even though this is sound, here somehow you may be able to cheat? Why is it? So what is the guarantee of the MIP? The guarantee is it's sound, assuming that the provers do not interact. Or more specifically, it's sound if the provers behave locally. So prover 1's answer is a function of query 1 only. And prover 2 answer is a function of query 2 only. What does that's on the left. What guarantee does semantic security offer us here on the right? The guarantee that it offers us is that when you look at query 1 and answer 1, it basically should not give information, it should not leak or signal any information about this query, because otherwise it broke semantic security. That's the guarantee we get. So the guarantee here we get that you need to answer here in a way that doesn't signal. Turns out that it's different than being completely local, turns out. So here you get soundness, assuming kind of you use only, this guarantees that this prover here must use kind of a non-signaling strategy, namely that the answer he should not signal. And here you're guaranteed soundness only if you're local. Turns out the local and non-signaling, not the same. Okay, non-signaling, by the way, is a notion that was defined actually in the context of quantum mechanics. Okay, so what is true, though, is that if this MIP happens to have what's called non-signaling soundness, which I'm not going to define actually, but it's a more kind of a stronger notion of soundness, then this is sound. Now, you may want to ask, okay, so what is this non-signaling soundness? I'm not going to define it because I want to give you a different perspective that will kind of work better with the next pillars that I'm going to describe. But there is some definition. And now what you might ask is, okay, there's some definition of non-signaling MIPs. For which language do we have such MIPs? In particular, do we have for all of NP? And the answer is, well, we have for some, but not for all. We have for deterministic languages. We have for some, we have for batch NP and some extensions, but not all of NP. And there is a reason for that. Okay? You can't have all of NP. All of NP. You cannot have non-signaling MIP for all of NP. That's kind of succinct, with where the query size and the answer size are small. Okay, but I didn't say even what non-signaling MIP is. So now let me actually say what it is in a different language that than we usually use. Yeah.
Can I just ask, you cannot have it for all NP. Do you have a concrete counterexample attack?
Yeah.
Okay.
I'll get there. Yeah. Okay. I'll explain exactly that when we use kind of this new language. Okay. So here's a way to think of MIPs. That's not how I defined it with the two provers, but let me offer a different way of thinking about it that's actually equivalent. So you can think of an MIP as follows. Take your circuit that verifies the witness. Okay, so you have the circuit, you take a witness and checks if it's a valid witness or not. And now encode this circuit in some way. Okay, so add some wires and so on, add some encoding to the circuit. And now you can think of asking the provers some random points or the values of some random wires in this extended circuit according to some distribution. Okay, so that's how an MIP works. For me, an MIP, what it does, you take the circuit, you encode it, the verification circuit, you encode it in some way, and you ask the provers, each prover, let's say one wire, and you choose a few wires, let's say L wires. L should be succinct because that will determine the length of the proof. You ask them for some L wires in this extended circuit according to some distribution.
So what is the distribution on X?
No, it's on the wires. So fix X. So let's say I want the provers to prove to me that X is in the language. X is fixed. They say X is in the language. I'm like, okay, I want you to prove it to me. How are you going to prove it? Here's how I'm going to, me as a verifier, what I'm going to ask them to do. I'm going to take the verification circuit that checks if a witness is valid for this X. I'm going to extend the circuit in some way. And then I'm going to choose wires from this extended circuit according to some distribution.
Boolean to something.
To extend it, exactly. And you can think about it. You can say, wait, what is this extension? So think about it as follows. Before, for every prover, I had a query. So you can think of it for every possible query, I compute like an extension that computes this query. So compute the answer to this query. So for every query, you can add a little kind of circuit that computes the answer to this query. So the point is, this is kind of without loss of generality, because you can think of this extension if you want to be an exponential size. Yeah, so you can think about, exactly. So think about an MIP, the prover, given the witness, computes some answer, make this kind of computation be part of this extended circuit. Another way to think about it is more like a PCP, if you want, okay, for those who are familiar with the concept. But my point is that this extended circuit, it can actually be of exponential size as long as each wire is polynomial time computable. Okay, because I'm going to ask a prover, compute a wire. And as long as each wire can be computed in polynomial time, I have like an efficient prover. Even though this encoding can be of exponential size, because nobody actually needs to write down or compute this entire encoding. Okay, because all I'm going to do as a verifier, I'm also, there's some extended circuit, which is defined somehow, and I just choose a few wires, and I tell the prover, compute the value only of these wires.
I don't see why this restriction of polynomial time is equivalent to the model.
No, so good. So for now, I'm focusing, because I'm interested in SNARGs, I'm only focusing on multi-prover interactive proofs where the provers are efficient given the witness. Okay, okay, I want to focus on efficient provers because the talk is about SNARGs and we're interested in provers that.
Titles are confused. Okay.
Yeah, I'm focused on, and it turns out that actually the MIPs that were considered in the literature do satisfy it. Turns out, doesn't have to, but that happened to be the case. So it's not really a restriction given the history.
But it cannot be exponential because you want the communication to be.
Okay, it can be, and we'll talk about that. You're right, it will affect the communication, but it's still in a non-trivial manner. So I'll explain.
The query, but not the length of the answer.
Yeah, it's coming up in the next slide. Yeah. Okay, so in the guarantee we have that if the provers answer the wires in a way that's accepting for the verifier, then we know the circuit is satisfiable, namely there's a witness, okay, or it's in the language. Okay, so that's kind of the guarantee we have. Okay, I'm going to assume, and this is an assumption, but turns out that all the MIPs in the literature, actually this assumption holds, but this is an assumption, that actually the verifier checks, the checks the verifier does, is only kind of local consistency checks. So really the only thing the verifier does, he asks a bunch of wires and he checks that these wires are kind of locally consistent. So they are consistent with the gates among these wires. Okay, that's all he checks. Okay, and again, all the MIPs in the literature can be made to satisfy this. So it's not like a big assumption, but that's what I'm going to assume.
Sorry, where is the gap here? Why is this not without loss of generality for a
Because then you'll need an EF proof of completeness.
Oh, God.
Okay, good. So now okay, I'll get to Evgeny's question answered in a second. But basically, now let me tell you the designated verifier SNARG. So what is the SNARG? I have an extended, I take my circuit, I extend it, I sample some wires, I send it to the single prover with different encryption. So when he answers the value of these wires, he has no idea what the other wires are. They're encrypted with different keys. And I get encrypted answers, and I check local consistency. Okay, so the verifier accepts if the answers to these wires are locally consistent and are locally consistent with the output being 1, which is the claim. Okay, so that's the construction. Okay, that's kind of how I move from MIP to a SNARG. And now to Evgeny's question, what are the efficiency guarantees here that we get? So this is part of what I'm thinking of the CRS, even though it's designated verifier, so it's a bit weird to think of it as a CRS, but just to not introduce more terminology. So the CRS is the length of this. What is the length? Well, there's kind of O tilde for encrypting. O tilde, for me, the O tilde, it contains polynomially in security parameter, okay? Just in security parameter. But I don't want to deal with all the security parameter running around. So basically, it has L wires. Each wire to specify its log the extended circuit. So even if the extended circuit is exponential, This is still polynomial, but may be large. So if the extended circuit is of size 2 to the witness, then this is of size witness, which is what we think of as a log CRS. Okay. The proof, on the other hand, is just encryption of L bits. So as long as L is small, we're happy. And the runtime of the prover, he needs to compute the value of each wire under FHE. But again, we assume that the wires are efficiently computable. Each wire is efficiently computable. Okay, sorry. Yeah, sorry. I missed the beautiful terminology that Alex gave for me. So I want to think of an extended circuit that may be of exponential size, but where every wire is efficiently computable. I'm going to call it a locally computable extension.
The address of the wire?
And yeah, it's given a wire to compute the answer takes polynomial time.
Or you have some location?
Yeah, I'm giving you a location of a wire, and you need to give me the value of that location. And it should be a polynomial time. That's what we call a locally computable extension. So it can be an exponential size, but it's locally. For each wire, you can compute the answer locally. Yeah.
Talking about exponential width or exponential depth, because one of the two seems unlikely that you can do fast.
Yes or no? As long I don't want to talk about width or depth. As long as you compute each wire efficiently, I'm happy. I agree with what you're saying. How can you? Maybe yes, maybe no. I don't want to get into that. As long as you compute each wire efficiently, it's locally computable, and I can build a SNARG from that.
It's reasonable to think about it as just being large, but
Yeah, you can think about it as just being wide. Yeah.
Think of this as a read-solvent code with extremely good distance.
Exactly. You can think that's an example. Yeah, precisely. Think of it as just like a read-someone encoding or any encoder if you want. Yeah.
If you had a cheating prover, how do you know how many wires they'd have to lie about? Like, what's the chance of actually getting caught? Prover doesn't have a prover.
If the if the prover doesn't know what? Sorry.
Let's say you don't have an actual witness and you're trying to generate a fake proof. Like, the wires are basically how you audit them.
You're saying how would you cheat?
Yeah, what if there's just one wire that's wrong? Like, how many wires are going to be wrong in the circuit?
So okay, we encode it in a way that even if you're wrong in one wire here, you'll have to be kind of incorrect in many, many wires here. Basically, what this thing usually is like exactly said, like a aircrafting code of the computation. So even if one wire is wrong in the computation, you'll need to be wrong in many, many wires here, and therefore I can catch you locally. That's the intuition. Kabir, yeah.
What is the actual SNARG construction?
Good. So far, the construction is it's this. So it's not really a SNARG. It's a designated verifier. It's basically more like a two-prover, a two-message argument system, if you want. So the verifier publishes these queries. The prover, as a proof, gives these answers.
The verifier message is long.
The verifier message is long if the encoding is long. So if the what?
It would be.
We've seen both. It can be, it cannot be. We've seen, if you take like a BFLS type PCP, it's not long. If you take a Hadamard type, it is long. So there's both. Actually, for most kind of conventional like MIP or PCP, it's actually small. So, but we will talk about long ones because that's going to be interesting for us. Great questions.
Well, maybe it's not critical, but is it clear that this template is reusable? Right?
It's not reusable. Great. This template is not, it's not just clear. It's clear that turns out it's not. Because if I have X in the language for which I know a proof, what I can do, I can decide to cheat based on, I can say, well, if the first bit here is of Q1 is 0, I'm going to definitely cheat in a way that I know I'm going to be rejected. And if it's 1, I'm going to answer correctly. And then based on just observing if I'm accepted or not, I can learn. So it's not reusable. Okay, so this has about a lot of problems. Reusability is one. And indeed, when it was posed originally, it was thought of as 2-message arguments. So not like just turned later to be adaptively sound, but it's still there's the reusable issue. Yeah.
Yeah, can you also compare this with where we just unroll all the IP messages to a PCP, like this exactly like this?
Good. So you can think of an IP where you unroll the messages to a PCP, I guess any IP you can think of as a MIP. So think about if you have an interactive proof, you can think of, let's say, L rounds, you can think of it, at least public coin, you can think of it as an L prover MIP, where you give prover one the first message, prover two the first two message, prover. So an IP is just a more restricted form of an MIP. So this is kind of more general. Great questions. Okay. Good. So so the main question though, so it's designated verifier, which is a problem, the reusability, but is it sound? So now let me talk about soundness. And now I'm going back to like the non-signaling piece, non-signaling versus local and so on. So I want to explain it in this, with this terminology. So now, what is the soundness guarantee that we get? So here's what we can say. Suppose there exists a cheating prover that succeeds in cheating. So he gets these encrypted wires, he gets back answers that are accepting. What does that mean? It means that we can get out of him what I'm going to call a weak local assignment generator for the extended circuit. What do I mean by that? So I have here the extended circuit. What I mean is that I can, so what is this weak local assignment generator? Well, I can generate queries from a distribution, the verifier's distribution basically, and get assignments that are local assignments that are consistent. Okay, in that sense, it's a local assignment, but it's consistent only on average with probability epsilon, namely the prover's cheating probability, the probability that he successfully cheats. In that sense, it's only a weak local assignment generator. It generates an assignment locally, but it's not really a good assignment, even locally, only with probability epsilon over the distribution. Okay, so I can generate assignment for wires chosen from the distribution D and get assignment that are locally consistent with probability epsilon, the prover's success probability. And these assignments satisfy what we call a non-signaling guarantee. So what is the non-signaling guarantee? Basically, it says that if I'm asking him all these wires to give me answers, the answers, let's say he gives to these, the distribution doesn't depend on the other queries. Okay, so the distribution shouldn't signal, like it should be indistinguishable. You should not know from this distribution what the other queries were. And the reason for that is by semantic security, right? Remember, we put things under encryption. So if the answers here were different, whether you ask this question or this question, then you broke semantic security. So saying it a bit more formally, the non-signaling requirement says that if you ask for wires, let's say Q1 up to QL, and then you ask another wires, let's say you ask the red wires, and then you ask, let's say, the blue wires, which are denoted by Q primes, but let's say they agree on some subset S, that the answers you get from the red wires on S and the answer you get from the blue wires on the same set S is indistinguishable. Because again, if you can distinguish between red and blue on S, then you learn that these were the queries or these were the queries, and that breaks semantic security. Because these were encrypted with completely independent keys. And so that guarantees that you learn nothing.
Think of both of them as random variables and not definite answers, right?
Yeah, exactly. Exactly. The answers are indeed random variables. And I want to point out, even if the prover is deterministic, even if the original prover is deterministic, because we give him encrypted queries and encryption has randomness in it, the answers we get from him may be randomized. Once we decrypt his answers, they may be randomized, even though as a prover he's deterministic, because of the randomization of the encryption. And indeed, if he answers just deterministically, then he can't cheat. Like that, we're golden. But he may not do that. Yes, okay.
Is the reduction straight line or do you get to read YP stuff?
Okay, when I say a local, so the local assignment generator here, it's just, you ask a bunch of wires, I send it to the prover, I get answers, and that's it.
So you just query the approval.
Yeah, that's it, right? It's like simple.
But what is weak?
Okay, the weak is that the local consistency only happens with probability epsilon on kind of on average over D. Over the distribution that,
One query where you're really good at versus one that you're bad at.
yeah, there may be queries that you fail, there may be queries that you're good, but on average, you're good with probability epsilon. Okay, and that's important because what we actually get from it is a local assignment generator, not weak, on the actual tableau. Okay, so basically this encoding, what we use it for in the analysis, what we use it for is to get a full-fledged local assignment generator. And what I mean by full-fledged, here we have local consistency everywhere with very high probability. And basically the way we get this is, the encoding is like, it's like an error correcting code of this. So basically the value of each wire we get by, checking and asking and then coding on random wires. So there's kind of this use, which I didn't talk about and won't explain, but there's an implicit use of error correcting codes to go from local consistency on average to local consistency everywhere. So basically the guarantee we get is that on the circuit and the verification circuit itself, every L wires you ask are locally consistent with probability like 1 minus negligible. Yes, Kabir?
Still only checking a few wires.
L wires, yes. It's a little less than L, but so if I have L here, he'll have L divided by polylog. Yeah, it's basically the same. Yeah, by the way, there's some details that I'm gonna not mention because just to keep things focused, so that's one of them. But yeah, think of it as L wires, some local. And the more wires you ask, the bigger the proof becomes. So you don't want to ask too many. If you can ask all of them, and then that local consistency just means correctness and you're done, but that will make the SNARG of size all the wires. So that's no good. Great question. Okay, so we get the local assignment generator. The definition is that you get local consistency everywhere for any L wires. You get local consistency with probability almost 1. And also you have the same non-signaling condition as before. So namely, if you ask these wires or you ask these wires, the answer you get here, if you ask with the yellow wires or with the red wires, it will be distributed similar. And if it's deterministic, it's the same. Okay, and this guarantee is, again, something we get as a gift from semantic security.
So you kind of went from like very weird distributional questions to any LY.
Exactly.
So it's an overkill, but it's good enough.
Exactly. And if you think about it, that's how the analysis is done in PCP or an MIP. You have like this average case, and you go to kind of worst case on the actual computation. So this is similar just in the non-signaling setting. Yeah, great. Okay, so of course the question is, the fact that we have a local assignment generator doesn't mean that we have soundness. Our goal is to prove soundness. So the fact that we have local consistency, does it imply correctness?
Error is small enough to have union bound, right? Or not really?
Again, sorry?
Error is small enough to have union bound on all gates or not?
You're talking, okay. So.
But union bound doesn't work.
You're talking, okay, first of all, it makes sense if you think about deterministic computations, I think. So I'll say a word about that in the next slide, okay? I think it's what you're asking. If not, we'll go back to it. But first of all, the question, does it imply soundness? And the answer is not for all of NP. It's exactly for the languages I said before, okay? And in particular, it is for deterministic and some non-deterministic. So now going to your question, Tavishai's question, for deterministic languages, it does imply. And why does it imply? Basic idea is, well, you know, these wires are consistent with the input, so they're correct. They're correct, and this is consistent, so this is correct. Similarly, this is correct. These are correct and consistent, so this is correct. You go all the way to the end. Even here, this is not actually true because there's a blow up of error. So this is correct, remember, with all but negligible probability. And this is negligible. These negligible double things blow up. But turns out if we encode this computation a little bit, we can make this argument work. Was this what you asked about? Related to what?
Yeah, because I guess these random variables don't necessarily live in the same probability space. Right?
Exactly. Because they're not identical, is the point. You know, when I say this distribution and this distribution, they're not the same. They're indistinguishable. And this thing, nothing is perfect. So it's like you need to account for these errors that blow up.
But they're indistinguishable computationally.
Yes.
So this statement though is for all deterministic languages?
Yeah. For any deterministic language, so if you have here X, and you have a local assignment generator that tells you that CNX is 1, this is just kind of the deterministic computation. Local assignment generator with locality like polylog, the circuit size implies correctness.
Correctness for computationally bounded proof.
So now, okay, I started with a computationally bounded prover implies local assignments for the tableau that are non-signaling. Now the claim is if you have a non-signaling locally consistent assignment, it implies, for deterministic languages, implies that the output is indeed 1. So I started with a cheating prover that's polynomially bounded, but then I forgot about the bounded and I got local assignment that's non-signaling. Non-signaling meaning that if I ask the value for this with these wires or the value for this with these wires, I get the same answer, at least the distribution is the same. For that, I needed the prover to be polynomially bounded. But now I forgot about the prover and I just have this non-signaling and local consistency.
So you're saying it's not perfectly non-signaling?
It's not perfectly non-signaling, it's not perfectly local. I mean, I define non-signaling to be indistinguishable. So it is indistinguishable.
But how could it be? If you have this indistinguishability relaxation, and yet your statement does not require computational restrictions on anybody.
So, okay, so what I am assuming that my cheating prover for the FHE is bounded. Yes. Yes, I am assuming that he's bounded, for sure. Otherwise, I can't argue this non-signaling guarantee. Yes, yes.
That's what I meant by correctness with respect to.
Yes, I'm assuming that my cheating prover is computationally bounded. This implies this non-signaling criteria. And this non-signaling criteria I use in order to argue that if you have some local assignment generator that's non-signaling, the output is 1 for deterministic languages.
You need the extension also to be.
I need the extension because otherwise the error blows up. So,
Extension is also deterministic then.
yeah, there's some extension. Yeah, I don't want to go into it, but yeah, basically,
Like
yeah.
Whatever. The other
Oh, no, not that extension. No. So basically you can think, no, it's almost true that so the idea is if you're local consistent, this is correct. If this is correct and this is correct, this is correct.
So you're only using local consistency on the original blue part of the circuit.
Exactly.
Extend the circuit.
Right, just that. However, I need this blue circuit to also have a minor encoding, like a hash of the wires. Because otherwise there's error blow up. So the correctness is 1 minus negligible. So here you have a negligible probability of failure mu. Here you have also mu. So here it becomes 2 mu. 2 mu, 4 mu, it blows up. So you need to do something to fix this. There's a way to fix it with like a little extension to this blue tableau, but I'm omitting this. Just saying there's something to do. It's not trivial, but you can tame the errors here and make it work.
By just squashing the circuit to be logarithmic depth? Or?
No, by adding kind of hashing all the wires in the center.
Basically squash it, because you only need to verify the hash?
Yes,
You can think of it that way. You can think of it that way. Yeah. Okay, how about NP? Okay, so it turns out you can do it for P, for deterministic languages. What about non-deterministic languages? For non-deterministic languages, it turns out it's just not true in general. So I can actually come up with languages that are in NP and X is not in the language and there is a local assignment generator. Okay, and in particular, it's not true for languages in NP that are very hard. What do I mean by very hard? Languages that you cannot decide if X is in the language or not in time n to the locality, the number of wires in the local assignment generator, the locality of the local assignment generator. Now, why is that? So again, I'm saying if the language is really hard, if the NP language is really, really hard, like 3SAT, then even for X not in the language, there exists a local assignment generator that like is consistent with being 1, with the output of the circuit being 1, which is false. Why is that? So the reason for this, it turns out that deciding what is the maximum success probability of a local assignment generator can be done in time roughly n to the L. And basically there's a linear program that computes the value of the best local assignment generator. So now if X is in L, you have a local assignment generator which succeeds with probability 1. But now if X not in L, it's small, then you distinguish. So that's why for hard languages, the local assignment generator, the value for X in the language, not in the language, should both be 1. Otherwise, you distinguish X in the language and not X outside the language in this time. So basically, showing why there's a local linear, so you can decide that via linear programming. Actually, I can show you the linear program in like 5 minutes, but given we don't have much time, I'll skip it. But the basic idea that I want to convey is that the fact that there's a local assignment generator implies soundness for deterministic languages, but it does not. And by the way, for deterministic languages, the L here is like polylog the time it takes to deterministically decide the language. So indeed, this is bigger than T, the time it takes to decide the language. So for deterministic languages, local assignment generator, the existence of a local assignment generator with locality polylog implies soundness. For non-deterministic languages that are really hard, it does not imply soundness. Yes?
So just to clear, this is much stronger than saying there are counterexamples. This is saying for every language not in D,
yes,
there is no way to do
yes, exactly. For every language that is really hard, it won't work. Exactly. Great. So it's not like a contrived thing. Okay, so here the point is, this will take us so far. Okay, you won't get all of NP. You're stuck with this n to the, with languages that are decidable in time n to the locality. Okay. Now let's move to a new line of work, which started with beautiful work of Chuduri and Abhishek Jain and Zhengjong Jin on doing SNARGs via hash-and-BARG. Yes.
Maybe I missed this, but it is one thing to say that you cannot get a SNARG for languages that are very hard via this pattern. It is another to say that you can get it for languages that are only hard.
Good.
So can you actually get
Good. Okay. So what the Kshita is saying is she's saying, okay, you're stuck in and languages that are not too hard. But can you actually prove soundness for all languages in NP that are not too hard? And the answer is no. I can prove it for batch NP, for NT-ISP. Not all. It's going to be an open question in a couple of slides. But yes, no, I can't prove it for all. But there's a hope to prove it for all. Why not? It should be true for all. Maybe, I think so. I don't know. But we don't know how to prove, but definitely not beyond. Okay, great question. Great. Okay, so let me move on to the next pillar, which turns out to be a very similar pillar in retrospect, even though I did not see it when it came out, which is the hash-and-BARG. Okay. So what is the idea of a hash-and-BARG? The idea is the following. The idea is you take the verification circuit here's what the prover does. So the prover needs to give you a succinct proof. Here's how he gives you a succinct proof. He will compute all the wires of the verification circuit. No extension, nothing. Just compute all the wires of the verification circuit. He's going to hash it using a succinct hash that's locally, you can open locally, and with kind of, you can even extract a little bit. That's somewhere extractable. You can extract a few, the value of a few wires. Of course, not all, because it's a succinct hash. So you hash all the wires using what's called a somewhere extractable hash function, a hash function that you can extract the value of a few wires, but not too many. How many? Let's call it L. We use already L for the locality, L wires. Using a trapdoor for the hash. Yeah, so the hash key has a trapdoor. Using the trapdoor, you can extract a few wires. Good. And so you hash that, and then what you do, you add what's called a BARG, a batch, a SNARG for batch NP. What is the batch language? The batch language says for every gate, there's an opening for the inputs of the gate and the output of the gate. And these openings are valid and satisfy the gate. Okay, so now note the NP here, the witness for this NP is very small. It's just like an opening for the three wires. That's it. So it's very small because the opening here is very small. Okay, great, that's it. So and do we have a BARG, this batch, this SNARG for batch NP? Yes, that was their contribution. Okay, they gave us a SNARG for batch NP. Thank you very much. And publicly verifiable, yeah? No, they used actually Fiat Chamil, which is kind of what Alex glossed over too fast. Okay, so good. And their SNARG for batch NP, the size is like one witness, which we said is very small. It's just the opening of 3 wires times some polylog. Okay, so basically small. Great. And under LWE, they constructed it under just the polynomial and LWE. Fantastic.
Don't you need some kind of redundancy in the circuit?
It's the same. You need to, yeah, there's the same issue that like to tame the errors, you need to like a little bit encode there, and I'm kind of glossing over it. Yeah. So actually, let me tell you the guarantee you get. The guarantee you get is exactly as before. If you have a cheating prover, you have a local assignment generator on the circuit that you hashed in BARG. So whatever circuit you did, that's your guarantee. So it's exactly the same guarantee as before, no difference. And why do you have a local assignment generator? Well, it's exactly what you prove. You prove if you want to locally extract L wires, you take a hash function that's locally extractable on these L wires. And the BAR guarantee tells you that you're locally consistent. So it's really gives you that immediately. And the non-signaling, again, I don't want to get into it, but the non-signaling comes from the fact that you do not know where you are extractable on. This extractability gives you kind of the summer extractable hash. Inside it gives you this non-signaling guarantee.
So what was your BARG guarantee, the result?
So
No, you're using something.
I'm using a BARG.
What was the guarantee?
The guarantee, okay. So BARG is just a batch, a SNARG for batch NP. So it says if anything, any NP, I can batch where the length of the BARG is like one witness. So I can take what they show. The result is I can prove to you that X1 is in some NP language, X2, X.
Plus
The length of the witness. Yeah. Original was like times poly security parameter, and then it became better.
Okay,
but
so what is the NP statement here that you are barging?
Good. Sorry. The NP statement is that for each gate, I have an NP statement. And for each gate, the statement is that there's an opening to the input wires and the output wires of that gate that satisfy the opening of the hash, and is locally satisfies the gate. So it's a very small witness, it's just kind of the opening, which is, think of Merkle hash, it's very small. So the witness not here is very small. So I'm okay. The witness here is like polylog. It's just kind of the opening for each gate.
Wait, normal soundness? Isn't it just like some
Somewhere soundness?
Yeah, so you're asking is does hash and barg, is it sound? Yeah?
The BARG. The BARG.
Oh, barg is sound. The batch, the SNARG for batch and P that CJJ, that Abhishek Choudhury, Jain, and Jin constructed is actually sound. Not somewhere, it's just sound. It's somewhere extractable if you want, but it's sound.
I think he's pointing at the use of some kind
Adaptive
of
soundness.
soundness the way they
Yeah.
use it in the hash and barg, which is true, but it's
Like it's maybe sound
It's-
with no
it's-
adaptive statements, but
Yes,
adaptive ones.
there's an adaptive, non-adaptive issues here. Let me gloss over it.
And this is something you can do for all of NP.
Yeah, this barg you can do for, we have batch SNARGs for all of NP.
But it doesn't have to be NP complete. If you have an NP language with smaller witnesses, you get a smaller proof.
Exactly, exactly. You really pay only the witness. And even now we have even witness plus, like additive. Yeah, for the actual witness, not the instance, just the witness. The original may have been a little,
Matters, because you're given a BARG as a function of the, right, in this proof of.
no, but it doesn't matter here actually because the instance here is just a root. It has nothing to do with the actual X. The instance is the instance that I'm barging is, it has the hash of all this, and the hash is succinct. Let me call it a root or a digest. It has the digest and a G, like a gate. That's the instance. It's the hash and the gate, and the witness for it is kind of wires that the opening, and so it actually has nothing. I mean, the X is somehow inside the circuit, but it's not a, yeah. But anyway, by now, I don't remember the exact parameters they had in their paper, but by now we really have a BARG, which the actual witness plus poly lambda. So, we can, okay. Okay, good. So that's hash and BARG. And surprisingly, it gave the exact same guarantee that we had before for this designated verifier 2 message, whatever you want to call it. So with the locality, which is the number of wires you're extracted on in this hash function. So where are we? Where are we so far? We've seen 2 approaches. We've seen the MIP, the multi-proof interactive proof with FHE, and we've seen hash and BARG. Well, what do they give us? Where are we? So first of all, this is better. It's publicly verifiable. This is privately verifiable and has a rejection sampling problem. This is just better. The soundness guarantee they give, or at least what we utilize so far, is actually the same. It says if you have a cheating prover, then we can get from it a local assignment generator on the tableau that you extended or that you hashed in BARG, on the circuit that you extended or you hashed in BARG. So it's the same guarantee. Now, does this guarantee implies soundness? Sometimes yes, sometimes no. And this depends on deterministic languages, yes, non-deterministic sometimes, not all of NP, some of NP, there's these results. Such notion, by the way, of soundness is what's called in the literature a quasi-argument, just for.
Sorry, what's the difference? Like, yeah, it's not an assignment generator, so why don't you also have the same barrier that you can always do it in the error?
You can, which is why it doesn't give you. It doesn't.
So it doesn't extend.
Doesn't extend. No, it doesn't extend. Yeah, exactly. Quasi-arguments, exactly like you said, it implies soundness only for these languages, where L is the locality of this local assignment generator, and it won't extend. It's really, this is a barrier. And going to the Kshita's question, we don't even know, actually, if you can prove soundness for all NP languages that are not too hard. Okay, we have some example, not all, so this is still open. Yes.
Can you clarify if like this implication of like construct assignment generator, is it like a proof strategy or like is this something inherent with the protocol?
Okay, so what you're saying is can you, the fact, let's say if you look at hash-and-BARG, maybe you can prove soundness without going to local assignment generator. Maybe you can prove it another way. Okay, I think if you use like if you use the BARG and if you use these primitives as a black box, like the only thing you use about them, what I'm saying now is not something I proved formally, but that's my intuition, is that if you only use the hash and barg as like black box, you just, gives you soundness and it gives you, then I think it really boils down to, that's really all you have, like a local assignment generator. I don't think you can squish more out of it. From the MIP and FHE approach, you can actually squish out more, because if you remember, what it promises you is this weak local assignment generator and the extended tableau, which can be of exponential size. We show that implies a local assignment generator on our little circuit, but you can, like, why do we restrict ourselves? Like, we could have maybe worked on the extension and got something more. Okay, so in this we may be able to get more, but we didn't so far. Great. Yeah, Kabir.
Maybe I'm just completely missing something, but this seems like this local assignment problem is happening just because we're using a circuit structure. But if you were using like a PCP, there we know that if you're able to generate answers to the PCP on these just L-many.
No, because a PCP, it's not because of the circuit structure, because in a PCP you assume that the PCP is written in the sky.
Okay.
So like non-signaling PCP, where it's not written in the sky, you're stuck with the same barrier. So in a standard PCP, you assume someone writes this entire PCP in the sky for you. It's sitting there, and the verifier just gets to access a few queries.
Isn't this hash-and-BARG also doing something? You write the whole circuit wires in the sky.
No, in the hash-and-BARG, what happens is you can run the cheating prover and get L wires. And then you run the cheating prover again, you can get L wires. But you don't necessarily have consistency.
Yeah, but isn't the same thing, even Killian has this problem, right? But they solve it.
No, in Killian actually, because it's interactive, because you rewind, if you open, you always get the same answer. Otherwise, you walk the hash, the collision resistance.
The commitment is fixed, right? You don't go past the commitment.
Here, every time you rewind, you get a different.
Yeah, every time you rewind, you get a different prover in a sense, right? Because he can behave very differently depending on what you give him. Yeah. So here it's like you're in a non-signaling world, not in the classical world, which is much more difficult to handle. Yeah.
This problem comes up, or it come up also if you have unique witness.
Yeah, good. It seems like maybe, well, maybe for UP, when the witness is unique, maybe you can do something like you did for deterministic and things are better. Turns out it's very difficult, and it seems not to help, even though it may. We're every once in a while we're thinking about this specific class. And intuitively, the reason why UP, unique witness NP, seems not helpful is because the problem is to prove soundness. When you're in the soundness regime, you have no witnesses anyway. And so it's very different. Like in deterministic, there's a notion, oh, this wire is correct. In NP now, anyway, you're with X not in the language. There's no notion of correctness.
So you have barriers still?
No barriers. I mean, yeah, so even UP, for hard UP, you won't be able, because you can't do it for any hard languages, including ones that have unique witness. Yeah. Okay, so I'm like, when did we start?
10 minutes past.
Oh, so I need to finish. Okay, so I don't have, okay. So let me just say a few words about the last barrier, okay? About the last pillar. Okay, so the last pillar, the idea is, it's very similar to the hash-and-BARG, but I'm not gonna just hash-and-BARG. It's combining the first two pillars together. What I'm gonna do, I'm gonna extend, but I'm gonna add to the, I'm not gonna extend, I'm gonna add to the, I'm gonna put an encryption of some extension in the CRS. Okay, so in the CRS, I'm gonna have an encrypted extension. And then what I'm gonna do, I'm gonna hash-and-BARG the circuit that this part is in the clear and this part is encrypted. Seems very weird. So I don't wanna, so this is just saying this, I hash-and-BARG this partially encrypted circuit. Let me skip it. Seems very weird thing to do. Why would I wanna hash-and-BARG like a partial, either I want to extend, so I'll give this extension, or I'll just hash-and-BARG. What's up with this? And the idea is, the reason I want to do it is, but remember we said that if I have a cheating prover, I have a local assignment generator on the tableau, which is now partially in the clear, partially on the circuit that's now partially encrypted, partially in the clear. Turns out that we can go from a local assignment generator to this partially encrypted circuit to a local assignment generator of the circuit, the extended circuit without encryption. Let me not say a word about how. It's actually pretty, nothing interesting going on here. But here's what's interesting. What is interesting is I can go from the cheating prover to a local assignment generator on an extended circuit where this extension is encrypted. This means that if the cheating prover succeeds, I can, remember, I'm doing a hash-and-BARG here. So it's publicly verifiable. Anybody can verify if you succeeded. So if you succeeded, you should succeed on any extension. Because otherwise you broke the encryption. You knew what it was extended in there. So if you succeeded on any extension. So now I can, from a cheating prover, I have a local assignment generator for any extension. Any extension. Wow. That's powerful. So I don't need to choose the extension ahead of time. And in particular, I can, in the analysis, I can change the extension depending on the instance in the non-adaptive setting. And I can change the extension based on the instance in an inefficient way. And by doing that, we managed to get like SNARGs, for example, for DDH, which is a hard language. So we managed to bypass the barrier, the N to the L barrier. Because DDH is harder than N to the L. L, there's going to be polylog. Okay, so, okay. We can also extend it to an exponential size extension as long as this extension is locally computable, because we don't actually need to put this entire extension straight up. We can put it kind of little by little. And this is where, even though I won't have time to show you, unfortunately, where we actually can use a non-black box technique. Okay, let me summarize. What? More?
Yeah.
This?
Yeah, this. So when you show this picture, that the bad guy, so there's implications.
Yeah.
Say that.
Yeah, good, okay. So I'm doing a hash-and-BARG on some partially encrypted circuit. The hash-and-BARG, the guarantee hash-and-BARG gives us that if you have a cheating prover, you have a local assignment generator to the circuit that you're applying hash-and-BARG to, which is this circuit. It's a partially encrypted circuit. What we show is if you have a local assignment generator to this circuit, it means you have a local assignment generator where we unencrypt this part. So you can generate kind of local, the values of the wire in a locally consistent way without the encryption. And now
the bad guy could do it. It's just that it exists.
It implies we can extract from the bad guy a local assignment generator. And now we can do it for every star because, because it's publicly verifiable. So he should be able to succeed no matter what star is in there. Okay, so let me wrap up.
Can you just mention a sentence about the non-black box? Like, so using the coded attacker or your...
Okay, I'll mention it here. Okay, so just to wrap up, we had MIP and FHE, we had hash-and-BARG, we had encrypt hash-and-BARG. The last two are publicly verifiable good. In terms of soundness, these only imply local assignment generator in Tableau. This implies local assignment generator for every extension, even exponential size, it turns out, even though I didn't show you, as long as it's locally computable. Now, the question is it true for every L for every NP language you can have, and for every X not in the language, do you have a locally computable extension that does not have a local assignment generator? That kind of, if you can prove this, you have SNARGs for NP. Because if you can prove, oh, here's an extension that does not have a local assignment generator, well, the prover implies a local assignment generator. That cannot exist, done. So all we need is to say, fix your favorite NP language 3 set. Every element not in the language, you can extend it in a way that does not have a local assignment generator. Now the question is this true or not? If it's true, then my claim is that this is sound, and the way we prove soundness is via a non-black box technique. If you prove this to be true, this has nothing to do with the BARG, right? BARG, it's just about local assignment generators. There's no crypto here. But if you prove this to be true, my claim is the way I prove that this is true is via non-black box. And I don't have time, but this is it. So.
So for every attacker, you can find an extension that depends on attacker?
I show, for every attacker, I can have a local assignment generator. And this local assignment generator, because a local assignment generator does not exist, quote unquote, then somewhere they're signaling, where I don't know. But I'm gonna non-black box, I know it exists. And that's where I break the soundness, like I break the FHE or whatever.
But the reason you to think you cannot do it in black box in a black box way?
I think you cannot do it in a black box way. Yes. I don't have time. We have an entire summer, so we can talk about it.
So this is based on an assumption that there exists such a thing, or you can prove it exists?
No, I'm my assumption is
you're assuming this. That
if you solve this open problem for me, then I have a non-black box proof. So all I need is you to solve this open problem. And this open problem is no crypto.
It's trying to show that for every attacker, there exists some like extension that messes up that attacker.
It's not. I want to say that for every X, there's an extension that does not have an attack, that does not have a local assignment generator.
The selection is open even if ease of X doesn't depend on X. Like in some sense, like the more important detail potentially is just that E is allowed to have exponential size. This alone actually both gets rid of the attacks and potentially gets rid of gentrifix.
Yeah.
Also.
So that solves it. My question was about what gets rid of the attack is the exponential size.
Yes, exactly.
Yeah, exactly.
The runtime of the LP is circuit size to the L.
Yeah. When you say the words without local, what do you mean? You have to prove there is no?
Yeah, if you prove here's an extension that does not, there is no local, you can't, if the value is 0, there's no local, you can't locally satisfy it, that's consistent with 1.
You also say one line about the size, why having a large size is okay?
Yeah, the reason having a large size is okay is, oh, you're saying why can, oh, because what happens when I don't actually need to encrypt this entire gigantic log size. What I need is for the local assignment generator is, let's say you want L wires, I only need to encrypt the part that you need in order to compute these L wires. And this is small, so that I need to I'll encrypt little by little. Yeah.
So if you think about an NP complete language, you're looking at the co-NP complete. The X not in L.
I'm looking at X that's not in the language, exactly. And I'm asking, if you look at the verification circuit that checks and says it's not an L, is there any way you can extend this circuit to be exponential size depending on X, not depending on X, I actually don't care, in a way that you cannot locally satisfy it in a way that's consistent with 1, with a fake, like with an untrue output? Of course, you can locally satisfy and say the output is 0. It's not in the language, okay? But I want to say you can't locally satisfy it in a way that's consistent with a 1. And I believe that my conjecture is that this is true. I just don't know how to prove it. Exactly, because now to solve a linear program of this will require time, the extension to the power of L, but the extension is exponential time, so. And we have more reasons to believe it's true, but will require,
You phrase it as local to global. You're saying that local assignment implies the global.
Exactly. Local assignment implies global, exactly. Yes, precisely. I didn't have time, but I also want to just mention that so far I talked about extensions that are like no crypto, but we can actually put cryptography here. And then we can get a lot of nice stuff. So I didn't have time, but maybe in the proofs workshop or some things, or someone will talk about it, because it's there's a lot of potential here with the encryptation bar that I didn't have time to talk about. Okay, thank you.
So,